All right. Hi, everybody. So last time we talked about um, doing these, calculating these area functions. And I had one more example at the end that I kind of wanted to talk about. So I'm gonna do that one here real quick before we take questions and start on some new stuffs. Does that sound okay to you guys? Whatever. Do you say so, Mr. Kulik? All right. So it says, suppose the odometer of our car is broken and we want to estimate the distance driven over a 30-second interval. We take the speedometer readings every 5 seconds and record them in the following table. So how are we going to figure out the distance traveled with this information? So let's kind of imagine what we have here. So if we plot this function, the x-axis is our time function, or is our time variable, and the velocity is like over here. Well, let's just say and the velocity is in miles per hour. What do you recognize right away that's going to be an issue? Yeah, the units aren't matching up. So probably first things first, we'd want to square that. So what do you think is going to be easier? Should I convert the velocities into per seconds or the times into hours? Right, either one would be fine. Everybody agree with that? Either the time has to turn from seconds to hours, or the velocities need to turn into like miles per second. What do you guys think? Yeah, I would turn the velocities to seconds also. I don't want to muck around with like itty bitty teeny decimals there on the second side, turning those seconds into hours. Everybody agree with that? That's my whole motivation, though. It doesn't really matter, but I'm going to just choose the one that seems the least annoying to deal with. So to convert these guys into per hours, what do I have to do? I know 1 hour is 3,600 seconds, right? Well, that's still going to be kind of stinky, though, right? Those are still going to be pretty stinky looking decimals. You know what else I'm going to do? I'm going to turn that velocity into just feet per second. It doesn't give me any direction as to like what unit they want this distance in. So I'm free to do it in any unit I want. I'm going to do this because, well, it's going to keep the units from being like just wacky tiny decimals. So I got about 25 for the first one. Let's just do it all at once here. Do that. 21. Okay. And then 24. I guess I could start recording these here. I'm just going to round these to the nearest whole number because it's well, it's probably good enough. If you hung on to the decimals, that would be okay. But I think that feels excessive for an example. I mean, you guys will get the idea with whatever I do here, right? 43 and 32. 1 and then 28. So let's see, 47, 46, 41. So if I'm just kind of doing like some kind of rough approximation here of like what these things are going to look like. That's kind of what my function is going to look like, right? Everybody's okay with that? So it kind of looks like that. So keep in mind the height for this or this area, or this this three-dimensional figure, not three-dimensional figure. This region is in feet per second, and the base is in seconds. So when I multiply these two things together, what unit am I going to be getting? Yeah. So this does seem like, if I calculate the area under this curve, that is going to give me the distance traveled. Everybody buy that? Okay. So I know that each of these bases down here the delta x is 5 seconds. How can I tell that?
It's a change, 5-second change in time.
Yeah, I'm just looking at the table and looking at the change in time is constant throughout the entire sample. That's great. So all I'm going to do then is calculate my area. I guess I'm left with the choice, should I be using a left-hand rule or a right-hand rule? I don't think it really matters here. Again, they didn't specify. And I suppose if we really wanted to, we could take both of them and look at the average. Would probably be our best estimate. So maybe we'll do that. So I'll do the right-hand rules first. That's going to be 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 46 times 5 plus 41 times 5. And if I do the left hands, I'm going to have 25 times 5 plus, and then I'm just going to cheat here a little bit. Let's just do that. Everybody's okay with me cheating a little bit?
Remind me again, so how do you get the first value for the left hand?
So I'm gonna use, oops. So this is the height for the left. So that's the 25.
Oh, it is, yeah.
So I'm making that rectangle. And then for the right hand, we're using that as the height. So I'd be drawing that rectangle first.
Okay.
But it's, they're both approximating the same thing. Just one will be an underestimate, one will be an overestimate.
Yeah.
And
Average both.
if we average them both, that's probably going to be pretty good. So at this point, it's just a punch this through on the calculator. So 31 times 5 plus 35 times 5 plus 43 times 5 plus 47 times 5 plus 46 times 5. Oops. 47 times 5 plus 46 times 5. So 1,010 for my right hand. I guess those are feet. And then if I do the left hand, oops, I forgot that last one. Shoot. 41 times 5. Okay, 1215 is that. Okay, and then we'll do the other one. And there I've just replaced the 41 times 5 with a 25 times 5. So that should be 1135. And then if I average those, my best estimate there is going to be $1,175. So we'd say about 11 or 1,175 feet. Mackenzie. Because we took the left hand. So like again, our first rectangle when we did the left hand, we drew the blue rectangle. So the height there is 25. And then the right, and when we did the right hands, we drew the green rectangle, so we didn't use the 25 at all. Sure. So if I'm looking at this interval here, from 0 to 5. If I'm using the left hand, I'm using the left hand endpoint. So I'm using f of 0, which is 25. If I'm using the right hand rule, I'm using the right endpoint, which is f of 5, which was 31.
Okay.
Is that?
Yeah, that makes more sense.
Sure, yeah. And again, like totally reasonable questions, like not dumb. Important that we understand the notation, like what this means when we talk about the right hand or left hand. Like if it's not clear, ask. Be happy to spell it out, right? Okay. So there's that. Everybody feel okay doing that one? If we wanted a better estimate, what would we have to do? We'd have to redo the sample, taking readings every 4 seconds or 3 seconds or 2 seconds or 1, you know, just like more samples where the change in X is smaller is going to give me a more accurate estimate, right? Ideally, how small would I want? Infinitely small, because then it's exactly the right value, but good luck doing that. Does that feel okay? Okay. Did you guys want to ask anything about the homeworks? Yeah, Blake.
With this in mind, do you mind just doing number 13?
Not at all.
I believe the data sheet.
Okay. Let me pull up the problem. Five one, number 13. Okay. We'll just drop in a new page here to house this stuff on. So it says the speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half second intervals is given in the table. Find the lower and upper estimates for the distance that she traveled during these 3 seconds. So when we ask for a lower and upper estimate, what are we really asking for? We're doing the left and the right sums. Okay. So we'll do the lower estimate first, which is the left-hand sum. So that's going to be using the left rule. So that's going to be the first one. And our delta x here, we can see from the table, and it tells us in the problem, it's going to be half a second. I notice the unit for my velocity is already in feet per second, so I don't have to do any unit conversion there. So we're just ready to roll. So I'm going to have delta x times the height plus delta x times my next height. And I'll just go all the way down, but I'm not going to take the last one because the last height is the right hand for an endpoint, for the last endpoint, or for the last interval. So I don't need that one. And then if I do it using the right hand, I'm going to skip the first value. So I'm going to skip 0 and just take all the rest of them, including the last one. And rather than recopying this all, I have the technology to do it. So why not just drop that in there? And then we have one more to add on at the end, right? Oops. I got an extra one in there, didn't I? But I did. There we go. Sorry. I started writing it, and then I was like, why am I writing this? I should just copy this in. And then I forgot to erase the thing I said. So you guys saw what I did. And now it's just plugging and chugging here, right? I'm going to skip typing in the 0.5 times 0. Everybody's cool with why? Because it doesn't really matter. So there's my underestimate. And my overestimate is going to be the exact same thing because I didn't even bother typing this one in, right? Just plus my last one. And there's my over. So we're between 34.7 and 44.8 feet. Mia? Oh. I think we're done, right? Yeah. That's 17? Okay. Grab that. All right. Says the velocity graph of a braking car is shown. Use it to estimate the distance traveled by the car when the brakes are applied. So let's just go ahead and I guess for where we're at, I would probably suggest even drawing what it is that we're about to calculate. Does it tell us whether we should be using left hand or right hand rules? Doesn't. Does it matter? Not really. Now remember when we did this, we looked at the left hand rule and the right hand rule, but really you can take any height. What might be better in this case, since we have one is an overestimate, one is an underestimate? If we used midpoints, so what I would probably do is I would probably do something like that. I'm just going to use 1 second intervals. I'm just going to use a midpoint to kind of estimate my height. Oops, that did not, that erased more than I wanted it to. Okay, good with that. And I'm just going to estimate the height. I'm just going to write it above, just so I have it written down somewhere. So I don't know, what does that look like? 58 or 59 to you? Does it really matter? I don't know that you can really tell. I'll call it 58. This one looks about dead on at 40 though. What's that at? Looks like that's probably just about 30. Looks like halfway in between 20 and 40 to me. That one is, I don't know, maybe call that 18. That one I'll call 10. And that one looks like about half a 10. I'll call that 5. So my distance is just going to be 58 times 1 plus 40 times 1 plus 30 times 1 plus 18 times 1 plus 10 times 1 plus 5 times 1. Since they're times 1, where I'm just using a 1 second as my base of my rectangle, I'm not even going to bother writing the 1 seconds. I'm just going to add that stuff up. So what do we got? 85, 95, 103. So it's 161. Ish. Say approximately. Now, is your answer going to dead on match the back of the book's answer? Probably not. Even if you did midpoints as I suggested here. Why? Yeah, we just eyeballed all of these. There's not enough, not enough grid line on the graph to tell exactly what those things are. So that's fine. If you're close. When I actually looking in the back of the book right now, it has 155 as what they came up with, which is, I think, close. 161, I would say, is close enough for that. Yeah, Blake?
So for this problem, so you chose to use midpoints. What's a sign that you should use midpoints for?
Well, here's what I would say. I noticed that since this is like a strictly decreasing function, if I did all left hands, that's going to be that's overestimates every spot. Yep. If I did all right hands, it's going to underestimate every spot. If I do midpoints, I have like a little bit that underestimates and a little bit that overestimates and a little bit that underestimates. So that felt like a better option to me.
Okay.
Now, if I have a function that's doing both increasing and decreasing, there it matters a whole lot less. But in general, midpoint is going to be a little bit more accurate than left-hand or right-hand rule. But if you had a problem like the previous one, can you do a midpoint on this? No, because all you have are the points in the table. You can't guess anything like we could with the function.
Is the midpoint, and then in the last example that you just did, before the homework.
Yeah.
So you use both the left and the right. Is that more accurate than
No.
the midpoint? Or is that really just finding, isn't that just the same kind of thing as finding the midpoint?
Yeah, I would expect a very, very similar answer. Again, I could not use a midpoint because I had a data table. I wanted to draw a picture for us to kind of connect it to what we had seen before, but I had a data table, so I couldn't do a midpoint there even if I wanted to.
Yeah.
Mackenzie? Sure. Just shrink that down a little. So it says, use definition 2 to find an expression for the area under the curve for y equals x cubed from 0 to 1 as a limit. So let's go back and look up what definition 2 was. I'll just screen cap it in for us so we can all be looking at the same thing. So that's definition 2. So it's just the limit as n approaches infinity of the right-hand rules. Okay. So my delta x is going to be the length of my the length of my intervals. So that's going to be the upper minus the lower divided by the number of subintervals. So 1 over n. So my area then is going to be the limit as n approaches infinity of, well, let's just write it this way, f of 1 over n times 1 over n plus f of, now how do I find the next point here? Yeah, remember x1 is like 1 over n. So x2 is going to be x1 plus delta x, right? Just whatever that last point you evaluated plus another subinterval. So 1n plus, or 1 over n plus 1 over n is 2 over n. I heard you whispering it, Mackenzie, which was great. Oh. Well, it was a girl's voice coming from that area. Sorry, I gave you credit. You should have just accepted it and been like, yeah, I totally saw it. Is this okay, though, what we're doing so far? And we're just going to do this, keep on doing this. So I'll do a dot, dot, dot. What is the, if we're doing right endpoints, what's the last endpoint going to be? Has to happen at 1, or I'm going to write it as n over n. So far, so good. And now I'm going to do a little bit of simplifying here because I know what f is. My function f is x cubed. So when I do 1 over n cubed, I'd get 1 over n cubed. And when I multiply it by n, I get 1 over n to the 4th. I do the same thing here. I'm going to write that as 1 cubed in the top. I have 2 cubed over n to the 4th, dot, 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 plus n minus 1 cubed over n to the 4th, plus n cubed over n to the 4th.
Why did you include not just the final value?
The second to last one? That's just kind of convention. Typically, that's what you do when you write like a dot, dot, dot. Is you'll have like 2, the first 2, and then the last 2. I guess I didn't do it up here, but I wouldn't mark it wrong if you didn't have it here. This is just kind of like practicing this generally, just to make sure that we get it.
Yeah.
You know what I mean? So I would say this is good for your answer for part A. Just take a quick peep at what they did. Yeah, so that's fine. If you wanted to, you could notice that, hey, I have a greatest common factor here of n to the 4th. Right? And if I wanted to, then I could write that part in the parentheses as a sum. So that's just the sum from 1 to n of n cubed. Now you don't have to do that. I would say from here on, all those answers I would count as, unless it was said specifically, show that this is equal to this, I would count those all as equivalent answers. They're all the same thing. It's just how much algebra did you want to do, or how like fancy did you want to represent things. I'd say those are all fine. Part B, it says the following formula for the sum of cubes of the first n integers is proved in Appendix E. Use it to evaluate the limit in part A. Okay. So that's really handy with where we left it, right? Because this piece I can just replace with this. Everybody cool with why I'm doing that? Tells me in the problem that's the sum of cubes. So I can just drop that in there. It was n times n minus 1 over 2, oops, n plus 1. Won't really matter. And then squared. Yes. We still have a little bit more to do on this, but yes, I'd be happy to do 19 also. Yep. So if I look at this, it says we want to evaluate this limit now. If I try to do direct substitution, what am I going to be left with? If I plug the infinity in. I have infinity over infinity, right? Everybody agree? That's one of our indeterminate forms. So how do I attack something that's an indeterminate form? Use L'Hopital. Now, the way it's currently written, I don't think is very L'Hopital friendly, because that second part that I just subbed in there, I have like a chain and product rule stuff going on. I would just do some algebra so I don't have to worry about doing chain and product rules. You guys cool with that plan? So if I just distribute things through, that's n squared plus n. And then if I FOIL that out, I'm going to have n to the fourth plus 2n cubed plus n squared all over 4n to the fourth. Now we're in a great looking L'Hopital form because all we have is a polynomial over a polynomial. And in fact, do we really even need to use L'Hopital to evaluate it now that it looks like this? What if we just do this? I can do it that way also, right? Could I do L'Hopital 4 times? Yeah, for sure. Not wrong to do that. Or I can just do this, which I think is probably easier in this case. Oops. And now when I do a direct substitution, I get 1/4. Everybody cool with what we did there? Again, there were some other opportunities to do some other reducings or like attack this with L'Hopital or, like take your pick. Any of those are appropriate though. We're developing a nice toolkit of options where it's a lot of these problems you can just do whatever you see as obvious. The key realization was noticing that this was indeterminate and you had to do something to kind of fix that before you could evaluate. Mackenzie, are you happy?
Yeah.
Sure. Did that seem okay? Pretty clear once we got to it? All right. And Sienna, you wanted to do 19 now?
Oh, yes.
Sure thing. Yeah, for sure. All right. So here it says use definition 2 to find an expression for the area under the graph of f as a limit. Do not evaluate the limit. So it's basically doing the same thing as 24. We're just not doing part B. Okay. Well, let's go grab our definition 2 so we can look at that while we're doing this. Okay. So the first thing I'm going to do is calculate my delta x, which is b minus a divided by n, where the a and b are just the endpoints of what I'm evaluating over. So that's 2 over n. So then my area is going to be the limit as n approaches infinity of f of 2 over n times 2 over n plus, and again, remember that like x1 is just delta x, x2 is x1 plus delta x, x3 would be x2 plus delta x. So we can just kind of keep plugging and chugging away at this. Oh, shoot. What did I do wrong? It's here. That's why I said, oh, shoot, because it means all the x coordinates I picked were wrong. Yeah, it's between 1 and 3. So what should I have here? Should be 1 plus delta x. So I need a 1 plus on all of these. The thing that I noticed when I looked, my oh shoot moment was when I looked at that last one. I'm like, that doesn't reduce down to 3, because I know that should be the last point I'm evaluating. Should be 3 if I'm using a right-hand rule. That was kind of nice, though, getting a chance to see, like, that's an easy error to make, right? I just made it without thinking about it. Because how many of these have started with 0? Almost all of our examples have started with 0, right? Okay. So then, what can we do here? So the limit as n approaches infinity of 2 over n. I don't really want to plug these in because look at that nightmare. But I need to do something with that. So what I'm noticing is that like delta x sub I would be like 1 plus I delta x. So if you think about it, we have, this is like the x-axis. It's like x1, x2, x3, x4. Well, let's make that x0, 1, 2, 3, 4. Like x4 is going to be x1, or it's going to be a plus 1, 2, 3, 4 delta x's. Right? So that's what I'm saying here. This is like my A, and then I'm going to add however many delta x's I need to that. And that'll always give me my end point of my interval that I'm going to be evaluating. F of. So if I look at what I had above, I'm going to just like factor out my delta x. Then I'm going to be left with f of, like 1 plus delta x, 1 plus 2 delta x, 1 plus 3 delta x, 1 plus 4 delta x, 1 plus I delta x. And there, that is what I'm going to plug in to my function, because that's just going to be like massively less stupid looking. Because I have and this is probably where I would leave it. And I elected to use the sum here because I didn't want to have to, it was going to just be a lot of writing that stupid fraction over and over and over again, a lot of like potential evaluating. Yuck. It's just a lot of writing. Not wrong to do it that way, but that's why I chose to use the summation, was just to get around having to write that over and over and over and over and over again. Because it's just like, why? Just why? If I'm clever and I can think about how to do it once, I'm going to just use a little bit of clever and do a little less writing. You know what I mean? I think that might have been all the homework. Was that all the problems I asked you guys to do? Or just about? Besides number 5, but you're okay with 5? Good. Well, that's okay. You guys, again, we can talk about all the homeworks. That was a normal amount of homework we talked about. Should we start then talking about 5.2? What do you guys think on that? Okay. All right. So 5.2 is largely like, at least the first big chunk of it is just like an info dump. So we're going to take these ideas that we had developed in the last section, and we're going to give them a name. So we just say, okay, let's say we have f, and that's just some function defined on the interval from a to b. And we can take that interval and divide it up into n subintervals where they have equal width, that width being b minus a divided by n. So exactly what we did in definition 2, right? From yesterday? Not yesterday, but last time. So we let, x0, which is a, and then x1, 2, all the way out to xn, which is the same as b, be the endpoints of these subintervals. And then we let x1 star, x2 star, xn star be any sample point. So it could be the left end, it could be the right end, it could be the midpoint, it could be some other, third point. like a third of the way through, or like, it doesn't matter. In fact, they could be randomly chosen even inside that interval. Doesn't matter. As long as that point lies on the subinterval. So if we do that, we define the definite integral of f from a to b as the limit as n goes to infinity of the sum from 1 to n of f of xi star delta x. Provided this limit exists and gives the same value for all possible choices of sample points, and assuming that limit does exist, we say then that f is integrable on that interval from a to b. So what we've defined here is a new calculus operation called the integral, or the definite integral. And that's what this symbol is here with the dx on at the end. What does that symbol kind of look like? Looks a little like the stretched out letter S. Why do you suppose we chose the stretched out letter S? What are we really doing? We're doing a sum. S for sum. S for sum. But that's that symbol. Okay, so what we've done is we defined a new calculus operation called the definite integral. So just a little bit of vocab here. So that stretched out S is the integral sign. The function inside our integral is called the integrand. The a and the b are called the limits of integration, where a is the lower limit and b is the upper limit. And the dx there at the end is just indicating what our independent variable is in the function. Almost always in this class it'll be, like x or y, depending on how you've defined your function. And then the procedure for doing this calculation is called integration. Now there's a whole separate course in calculus called multivariate calculus, where you can integrate or differentiate over multiple variables. So you have a function defined in maybe several variables, and you can do this over multiple variables.
How does that differ from implicit differentiation?
Well, that is, implicit differentiation is the derivative side. The integration side, you'll have multiple variables to integrate over, becomes quite a bit different. Why would multivariate calculus be important? What kind of world do we live in? Three-dimensional. How many variables are there in a three-dimensional world? There's 3, right? Yeah, everything is dependent on, every position of everything has an x, y, and z component to it. So you really have 3 variables going on. So it becomes quite an important branch of course in calculus, anyways. So keep in mind, this definite integral, it's just a number, right? The answer to this is a number. It's not an equation, it's not a variable, it's not a function, it's a number. And that number does not depend on x, right? So there's really no difference in the problem whether we write the integral from a to b of f of x dx, or the integral from a to b of f of t dt, or the integral from a to b of f of r dr, it's going to be the same number. It doesn't matter what you're calling the variable. Everybody's okay there? Okay. And then notice in our formula we had this sum. Right, if we go back and look up here, that sum was right here. Oops. That sum has a name. It's called the Riemann sum, or a Riemann sum, where Bernard Riemann was a German mathematician. Oh yeah, there it goes, German mathematician. He was, I believe, Carl Gauss was his his PhD advisor, and they worked together quite closely, and is maybe the most prominent mathematician of his era. So just a little bit of history, just squinting here, trying to see if he's on the board back there anywhere. Doesn't look like it. Gauss is, but Riemann didn't make the cut on the Hall of Fame back there when I bought my Hall of Fame mathematicians pack. Okay, so again, all we've done here is we've introduced a new symbol and done some vocab, right? We haven't done any, and the symbol that we're introduced is just shorthand for the sum that we've been doing up until this point in the previous section, right? So far, so good? All right. So if you look at, here's just kind of a drawing to reiterate what's going on. In this first drawing, we're looking at the sum of areas of rectangles. That's a Riemann sum. And in the second drawing, you're looking at the value of an integral, where it's the area under that curve. And we know that if you take infinitely small slices or infinitely small widths of rectangles, the area of those rectangles, it will be the same as the area under that curve, right? That's what we looked at in section 1. So if our function f takes on both positive and negative values, that means that it goes above and below the x-axis, like we see down here in this drawing, then the Riemann sum is the sum of areas of rectangles that lie above the x-axis, positive, and the negatives of the areas of the rectangles that lie below the x-axis. So we're going to think about negative area for those rectangles that lie below the x-axis. Everybody's okay with that idea? So when we take the limit of such Riemann sums, we get some situation here, like in figure 4. So we have some positive area above the curve and some negative area that's below the curve. So we want to calculate, or the definite integral is going to give us the net area, that is the area above minus the area below. Everybody okay with that idea? So we do have to be a little bit careful there, because we're going to have this notion of a negative area that just corresponds to the area of the that's below the, or under the curve, or between the curve and the x-axis, but below the x-axis. Is everybody okay with that? Probably not super surprising when we start drawing the picture. Negative area is not, or shouldn't be, a terribly confusing concept, but need to make mention of it, because in a geometric setting, it makes no sense. So in all of these examples we've looked at so far, these have all been integrable functions, functions where you can calculate the integral of them. That does not necessarily have to be the case. There are functions that are not integrable, and it refers to some examples from the homework in which that's the case. And we have the following theorem shows that most commonly occurring functions are in fact integrable. And this is a theorem that you'd prove in a more advanced course than like your introductory calculus course. It says that if f is continuous on some interval a, b, or if f has only a finite number of jump discontinuities, then f is integrable on a, b. That is, that its definite integral exists. So finite number of jump intervals. So when we say a jump interval, we mean something like that. Then you can't, that's not going to be integrable. What would a function like that look like? Right? So I would say your most common example would be a piecewise function. So like I'll say f of x is equal to 0 if x is a rational number, and 1 if x is not a rational number, i.e. it's irrational. So on the interval even from 0 to 1, we have an infinite number of jump discontinuities on that. So it'd be something like that. Does that feel okay? It would have to do something with this, with like a number set piecewise function to get an infinite number of jump discontinuities. And again, this would be something that if you took like a real analysis course, which is like the theoretical underpinnings of calculus, this would be something you talk about in a course like that, but way beyond the scope of what we're doing. But that would be an example of something that's not integrable. I spelled that wrong probably, but I did it messy enough so hopefully nobody can tell. That's the teacher's note-taking trick. It's just don't have good penmanship and then people can't really tell if you misspelled something or not. I think there's an extra E in there somewhere around there. All right. So we have if f is integrable on a, b, then the limit in definition 2 exists and gives the same value no matter how we choose the sample points. To simplify the calculation of the integral, we often take the sample points to be the right endpoints. So our definition of our definite integral just simplifies down to this, which is the same definition we saw in section 5.1. So you can, doesn't matter how you choose your sample point, as long as it's integrable. If that's the case, then let's just always choose to use right endpoints and just kind of standardize that process. So it just looks familiar to everybody and we're doing the same thing every time. Feel okay? Okay. So it says to express this limit of the sum from 1 to n of xi cubed plus xi times sine xi delta x as an integral on the interval from 0 to pi. Okay, so this is quite easy to do. So we're going to have our integral symbol. What's the lower bound on our integral going to be? 0. What's the upper bound going to be? Pi. What's our function that we're going to, or the integrand that we're going to be integrating, the function? So just x cubed plus x sine x. Notice I dropped the subscripts here. And then at the end, what do I need? In place of the delta x, I have dx. And that's it. No calculation involved. We're just practicing rewriting something from one form to another. Everybody's cool? Okay. Here we dump a bunch of summation formulas because to evaluate an integral, where we're at right now, we need to be able to evaluate these sums. The only way we're going to be able to do that is with these formulas that we're given. So you have 3 for polynomials, right? And then you have some like algebraic things. So like if I calculate the sum of a constant from 1 to n, it's just going to be n times that constant. Like if I add 1 up 10 times, it's 10 times 1, right? If I add 10 up 10 times, well, I can just factor off the 10. So it's going to be 10 times the sum of 1 added up 10 times. Or just like 10 times 10. Is everybody okay there? And I can do that, yeah. And if I have the sum of a sum, the summation symbol distributes. So I can just distribute it to each function part. Or if I had a difference, the summation still distributes to each function part. So these are the tools that we're going to be using to evaluate these definite integrals in section 5.2. By the end of this chapter, we'll have a much better way of doing this. But this is like the foundational work that we have to do to kind of, for this all to make sense. Okay. Part A says evaluate the Riemann sum for f of x equals yada, 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 taking the sample points to be right endpoints, and a to equal 0, b to be 3, and n to be 6. So I'll start by calculating my delta x. So that's 1/2 b minus a over n. I'm going to have 6 of these x points. So I have a plus delta x, a plus 2 delta x, a plus 3 delta x, a plus 4 delta x, a plus 5 delta x, and then a plus 6 delta x. Everybody's good with that? I stopped writing the plus the, I just wrote the answer. You know what I mean, guys? If we see the delta x is 1/2 and we're going from 0 to 3, 6, and there's 6 intervals, it's just like plus 1/2 each, you know, it's like whatever. I'm just trying to reiterate the formula as I'm talking through it, though. Okay, so my area is just going to be delta x times f of 1/2 plus 1/2. Well, let's just write it this way. We'll do 1/2 times f of 1/2 plus f of 1 plus f of 3/2 dot dot dot, and we'll write them all out, whatever. F of 2 plus f of 5/2 plus f of 3. And then I would say I would just go calculator time. So the function we were looking at was x cubed minus 6. So I'm going to be using the y equals on my calculator to make the evaluation of this go a little bit easier. So 1/2 times. Then I'm going to do vars, y vars, function y1 of 0.5 plus vars, y vars, function. Actually, let's do this a little bit smarter. We can do this a little bit easier, I think. Let's drop the parenthesis here and drop that there. Press enter, and I'll add to it the same thing, but this will now be 1. Oops. Got the plus sign. Go. Oh boy. Go to. What did I do? Oh. Hands. Ah. There. Okay. Then we'll just do second enter. There we go. 1.5. Second enter. 2. Second enter. 2.5. Second enter, and this is my last one. This is probably a little more convenient than typing it in all over again because it's just going to be a lot of buttons. But either way, you should get the same thing. So we get there about -3.39 whatever. Okay. Yeah. Part B then says to do this to evaluate the Riemann sum, or the, I'm sorry, not the Riemann sum, the integral. There's that. My delta x is going to be 3 minus 0 over n, or just 3n. And my f of x was xi cubed plus 6xi, and then I have my delta x, which was 3 over n. Everybody's okay here? So the 3 over n, notice, doesn't include an I, so I can, that's a constant with regard to the summation. So I can pull that out. And then I'm going to distribute the summation and use my summation rules to pull the constants out front. Then I'm going to go to my summation formulas. And I know that the sum of cubes was n times n plus 1 over 2 squared. And my sum of xi is n times n plus 1 over 2. And now I'm just going to work on evaluating this thing. But it sounds like I'm out of time. So you'll have to remind me next time to come back and finish up where we left off in section 5.2. I'll put the 5.2 homework up. Obviously, we didn't finish the lecture, so will you be able to complete the 5.2 homework? Probably not, but if you want to work on stuff that's like, okay, I feel like I got it for a while, and if it starts getting hazy, you can quit. Come back and ask some questions next time. Everybody feel okay? All right.